In this paper, we present NOPS, a novel approach to deal with the task of novel class discovery in 3D point cloud semantic segmentation. As the title suggests, the proposed method is designed to learn and address the challenges of novel class discovery within the context of 3D semantic segmentation. In novel class discovery, we work with a partially annotated datasets, where the labeled categories are referred to as base classes. In this example, road and vegetation points are labeled, while the rest of the points are unlabeled. Our goal is twofold. Firstly, we aim to learn the proper segmentation for the base categories. Secondly, we want to discover the correct classes for the unlabeled points, which we refer to as novel classes. In this specific case, the novel classes are vehicle and rider. In NOPS, we propose a methodology that merges the available supervision over the base classes with the pseudo-labels for novel points. These pseudo-labels are obtained through an online clustering method. By leveraging both types of annotation, we train a deep neural network to address the segmentation task comprehensively. The architecture used in NOPS is rather simple. Given an input point cloud X, we employ an encoder that generates point-wise features. Subsequently, two distinct heads are applied. The upper head produces logics specifically related to the novel classes, while the lower head predicts the logics for the base categories. These predictions are then merged, resulting in point-wise class predictions for each point in the point cloud. To optimize the network, we employ a standard cross-entropy loss function. However, it's important to note that the ground truth targets are available only for the labeled base classes, while they need to be defined for the novel points. To achieve this, NOPS employs the synchron-knop algorithm. This method operates in an online fashion and takes as input a set of points, represented here as features, along with a set of centroids that correspond to the weights of the novel head. The output of the algorithm is a clustering assignment that aims to assign the points to the centroids as uniformly as possible. Such soft assignment can be used as target for the novel points. However, for the method to work properly, we need to set up a swapped prediction task. This involves augmenting the input point cloud twice, passing both versions in the encoder and obtaining the soft assignments for both the branches of computation. Subsequently, the assignments for the novel points in the upper branch are used as targets for the corresponding points in the lower branch, and vice versa. Remember that the targets for the base classes are always available. In NOPS, we utilize a class balance queue as an additional component of our approach. This queue serves to store a fraction of the features from novel points in previous batches. At each iteration, we concatenate the actual features with the content of the queue. This combined data is then used as input for the synchron-knop algorithm. The purpose of incorporating the class-balanced queue is to address the issue of varying cardinalities of novel classes in each batch. By storing and reusing a portion of the features from previous batches, we aim to achieve better balance and stability during the training process. Another component that enriches NOPS is the filtering function phi, that dynamically selects features with the highest prediction confidence. It is applied to both the class balance queue, ensuring the insertion of informative features, and to the selection of the novel points that contribute to the network optimization. The evaluation of NOPS has been conducted on two well-known outdoor datasets, SemanticKITTI and SemanticPOSS. These datasets have been specifically adapted for the novel class discovery task. In fact, they have been divided into 4 different splits. Each split varies in terms of the subset of overall classes that are considered as novel, as depicted in the histograms. The tables here showcase the performances of NOPS in both SemanticKITTI and SemanticPOSS datasets, evaluated based on mean intersection over union. Our method is compared with EUMS, a method that originally addressed novel class discovery in 2D image semantic segmentation, and that we adopted for the 3D domain. In SemanticKITTI, NOPS outperforms the baseline in all 4 splits, exhibiting an average improvement of more than 5%. In SemanticPOSS, NOPS surpasses EUMS in 3 out of the 4 splits, with an average improvement of approximately 6.5%. In these images, we examine a split of SemanticKITTI, where the novel classes consist of road, sidewalk, terrain, vegetation, and building. As highlighted by the red box, NOPS exhibits superior performances compared to EUMS, delivering a more coherent segmentation of the various types of ground. Notably, both methods demonstrate decent results on the base classes. In this other split of SemanticKITTI, the novel classes represent smaller objects such as trunks. In this scenario, EUMS exhibits poorer performances, mislabeling the highlighted objects entirely. Vice versa, NOPS continues to demonstrate good performances, accurately capturing the smaller objects. Finally, this video focuses on the performances of NOPS in a split from SemanticPOSS. It is worth noting that how our method excels in accurately segmenting the novel class of pedestrians, here depicted by the red annotations. Thanks for watching.